So let me proceed. Number one, material for the final. I received some questions. Let me share just to have it clear to everyone. Share screen. Are we sharing the same screen?
Yes, doctor.
Yeah. The material is whatever in the slides, starting from the capacity of CISO, CMO, and MISO channels. Okay. I updated some versions. Up to the achievable rates of vector broadcast channels. The cooperative communications is reading. I wrote it reading because we didn't have time, to catch with it. It's not, that important. It's important, but not as important as the previous topics. The previous topics are the, the meat of the course. The essential topics of the course. Starting with the capacity of CISO channels, with CSIT, with non-fading and fading, sorry, and then fading CSIT and CSIR. Please, this has to be crystal clear to everyone. You will be asked in the final exam about CSIT and CSIR because this is, a very important concept in the course. It makes difference. In industry, they call it open loop, closed loop, isn't it? Yeah. If you have CSIT, it's closed loop. If you don't have CSIT, it's open loop, which is CSIR only. So it's very important, please. And the definitions of capacity there, the outage, the ergodic and the outage capacity. And related to the outage capacity, outage probability, and we use them for slow fading or delay limited applications, whenever we cannot do averaging. Because ergodic capacity is average capacity. If we cannot average, we have to use the notion of outage capacity based on, for a given outage probability. And we looked into CMO and MISO channels. Please, again, you should know the difference between them. If you can, MISO, CMO, we can always apply MRC, which we learned in wireless 1. And we also have seen in wireless 2. In MISO, it depends. If you can apply MRT, which is the version of MRC at the transmitter, you can see it. Then the capacity is the same. If we cannot apply or implement MRT, which is the CSIR only case, then no, they are not equal. The capacity of CMO is larger than the capacity of MISO. And then we looked into the channel models and the capacity of MIMO. Please, very important. Again, for fading and non-fading. You will be asked about MIMO again, and CISO and MIMO in the final exam. MIMO, single user MIMO, is the main part of our course. So I have to make sure that you understand it very well. It's the main, every course has objectives. It's recording. The main objective of our course is the single user MIMO. So please, you have to know the SVD. The formula will be provided for the SVD. So in the final exam, the ones who asked me about the formulas, you will have the SVD. You will have the capacity, MIMO capacity formula, and the formulas for the zero forcing and MMSE. The A matrix, all these formulas will be provided in the final exam. This is what you need. Again, the basic ones, you are supposed to know them. The definition of determinant, the trace. Please, the transpose. Don't tell me AT is not the transpose. Or the, how can I write SVD for real valued matrices? You don't need the conjugation. So the Hermitian will be transposed, isn't it? Am I right?
Correct.
Yes, doctor.
Yeah, please. And things like this, you are assumed to know them. Don't tell me, oh, I know SVD in the complex version. The real is a special case of the complex. You don't need the conjugation. You need just the transpose. So please, things like this, computing the eigenvalues. Some of you were missing this in the midterm. Please, you have no excuse. Linear algebra is very important for engineering. All engineering disciplines, just like Fourier and Laplace. You have and calculus. You have to know them. It's a default. Please, it's something very basic. And then we go to water filling in the eigendomain, because we do SVD for the eigendomain to get the R parallel channels. And then we perform water filling across the eigendomain. Okay? And the concept of eigenbeamforming, please, multiplying by V there and new Hermitian there, and starting with R and then mapping R into NT streams and so on. Please, the diagram is there, the descriptions is there. I may ask you about any of these. Please. I may ask you about the channel models. Why the IID model is widely used. Should be able to answer. Please, we are doing engineering class. Okay, so we are using these mathematical models for a reason. Why we care about correlated models? Should have an answer to this. Which correlation model is used? The Kronecker, isn't it? The Kronecker-based model. So please, you have to be prepared for this. The high SNR, low SNR, I'm telling you again, you don't have to memorize the expressions, but you have to know the comparison. You know, for example, at high SNR, both single user MIMO, the capacity will be proportional to R, pre-log gain, whether with CSIT or CSIR. You don't need formulas for this. It's a concept. Know it just as a concept. Okay? And you should be able to manipulate the capacity formula. You know, this formula, which will be given to you, you know, as we agreed in the formula sheet. This is the most important formula in the course. Yeah. If you have fading, you add the expectation, as we know. You have to be very familiar with this formula, and you may need to manipulate it in the final exam. Simple manipulations. So please be ready for that. This will be given. You don't have to memorize it. We agree. You know, but you have to know the procedure for the SVD. You have to know eigenbeamforming. The fact that the pre-log gain is R at high SNR. But do you need to know this expression? No. Just know the first one. Remember it, I would say. If you need these expressions, they will be given. Isotropic, you have to know it. Please. This is the second most important formula in the course. The isotropic transmission. We know why it's important, because it's widely used. Actually, whenever we don't have CSIR, most probably we don't have CSIT, sorry, we will use QX, and you have seen it in VBLAST, isn't it? Did you do the homework? So VBLAST uses this. Am I right?
Yes.
Is it? Yeah.
Yes.
So it's used in practice. It's very important. When is it optimal? Only for one case. We have IID Rayleigh fading channels, which is ideal, but we take it as a benchmark. Okay. Correlations, please. At high SNR, you know, I wrote once in one of the exams. I forgot about the exam. I wrote it, I printed a couple of days ago. But in one of the exams, I remember, I wrote correlations reduce, the MIMO capacity for all SNR, at any SNR, true and false. There will be true and false and explain in the final. Of course, you know this from wireless one. And the newcomers, please know it. I have always true and false, and you explain why is it true or false. So the answer is false. It's not true. At high SNR, yes, the correlations will reduce the capacity, but not at any SNR. At low SNR, actually, I told you we didn't discuss this. We have papers about it. They have shown that correlations may, for some scenarios, may increase the capacity. And there is a physical explanation for this, but I'll not go into that because we have limited time and we have to focus here. So please be careful. In engineering, we have to be specific. Don't go global in engineering. Be careful. And then so welcome the newcomers, Mustafa. The MIMO receivers, please, is a very important topic. The MIMO receivers. We didn't do much. We did the basic ones only. It can be a course by itself, MIMO receivers. As I told you before, you can find books about MIMO receivers easily. But we want the common ones, ML, and then linear, zero forcing, MMSE, and matched filtering. Matched filtering is rarely used, but it's considered one of the receivers, and SIC, successive interference cancellation. So I think we described, we discussed, we explained MIMO receivers, and I limited the discussion to be minimal. In a way, I didn't go into performance analysis. If you go into performance analysis, you can see it in our main reference. You can go and read there about it's involved. It requires some probability theory and advanced linear algebra and so on. Not very advanced, but still it's demanding. So we didn't go into that. So you have no excuse for MIMO receivers, please. Now we come to the capacity of multi-user topics beyond the midterm. Of course, they will be important for the final exam. Both, so you have to know scalar MAC, scalar BC, non-fading and fading, and the schemes used for each one of them. So please read carefully. Again, I recommend you make a tree, as we did before in one of the classes. MAC, single antenna, which is scalar MAC. Then non-fading, and then fading. Fading, CSIT, CSIR. And then name the schemes. Which schemes? Maybe more than one. Maybe OMA and SIC. Both will work. Like MAC, non-fading. You can apply OMA, and you can apply SIC, which is here. How does SIC compare to ML? Capacity region here. I explained it. Go back to the notes, to the recorded lectures, please. What's the sum capacity? You have to know it. The difference between the sum capacity and the capacity region. Okay, these are basics of information theory, very basic. And we care about the sum capacity. What if we have CSIR only? Have ergodic. Similar to the CISO case, it will be always less than or equal to the non-fading case. What if we have CSIT? OMA can achieve the sum capacity. Yeah, with CSIT. SIC will always achieve the capacity, the corners, huh? The points A and B. You remember? This is the two-user capacity region, but you can generalize it. What about opportunistic? There are some cases where opportunistic, choosing the best user for Mac and for PC. When users have identical channel statistics and power constraints, and they call it symmetric uplink. In that case, only in that case, you may maximize by allocating all the power to the user with the strongest channel gain. So you have to know, conclusion, you have three schemes, SIC, OMA, and opportunistic, or choosing the best user, the user with the strongest channel. When for both Mac and PC, when is it optimal? Each one of them. Okay. So please, this is important. If you have BC non-fading, apply superposition coding at the transmitter, which is the base station. Remember, broadcast is downlink. And SIC at the users. And you should know, how do we apply SIC? And how is it different from SIC for Mac? And how is it different from SIC for single user MIMO? I'm telling you, you have to be able to compare them. Yeah, no excuse. We did that before. And it's explained in the slides. Each one of them is explained. Again, for fast fading with CSIT, the sum capacity can be achieving by transmitting to the user with the strongest channel. This is similar to a Mac. Okay. These are some additional notes, some of them are conceptual, some are practical. They have to do with industry, NOMA, and these things. And what's special about NOMA and why is it attractive? We wrote a paper about NOMA. Now it has more than 500 citations. Amazing. So it means that NOMA is attractive, really. Can find it in my Google Scholar, really. We didn't expect this, but it indicates that NOMA is of interest, at least in academia. Maybe industry in the future, we will see. And then, because we mentioned about opportunistic, so I wrote two pages about opportunistic communication. And it's done in one chapter, by the way, in our main reference. I told you why, because his students, they worked on this at that time, the authors, students. And they casted this term, by the way. I think the opportunistic signaling, they called it. And even multi-user diversity, I'm not sure. Maybe they have casted this term. So please, I uploaded the lecture 19, I think, where I discussed, the details here, mainly this sketch, and the concept of the relation between, multi-user diversity and the shape of the BDF and the amount of fading, and the fact that the diversity gain, it's inside the log, please. Whenever it's inside the log, again, is diversity gain. SNR gain, you can see it as SNR gain. The diversity gain will show in the outage, isn't probability. You remember 1 over SNR to the power L? So this is how, I think I had a question about this. One of you sent it. What's the difference between SNR gain and diversity gain? You know, when it comes to the rate, it's the inside look gain. Some they call it SNR gain. Some they call it diversity gain. So, you know, there is no need for rigorous math about it. You know, whether you call it diversity gain or I would call it SNR gain due to diversity, if you want to be specific, you know. Yeah, but calling it SNR gain, sorry, diversity gain, there is no harm. Okay. But mathematically, the diversity gain is in the outage, not in the rate. Yeah. So this formally now, this is SNR gain. And the diversity is in the outage. But some, you know, researchers, they say, no, it's due to the diversity order is explicit there in the SNR gain. So let us call it diversity gain, and the SNR is B over N naught. That's the SNR. This is extra term. It's proportional to, for example, here, number of users, which is can be seen as the diversity order. And it's debatable. But for outage, no, it's not debatable. The 1 over SNR to the power n is a diversity gain. There's no discussion about it. So for outage conclusion, the diversity gain is well defined. For the rate, it's debatable, but it's not that big deal. You know, it's understood that the SNR improved due to diversity. Khalas, you know, not a big deal, huh? Yeah, please. And then we come to the vector MAC. The vector MAC and the vector BC are not easy topics to start with. However, we tried in here to approach it, you know, in a systematic and incremental way. Huh? We didn't do all the details. Some of them are advanced. I mean, the math details, but we did it conceptually, clear. So this is the common model. You have to be aware of it. You have to be aware of the sketch, aware and the expression. I may ask you for any. You have to be ready. And you have to describe it. Be able to describe it. What I mean, specify the dimension of every term. Even if you do the sketch, you have to tell me what's the dimension of X, what's the dimension of H, what's the dimension of Z, what's the dimension of Y. And here, experience in linear algebra, huh? Please. So this equation will not be given. It's easy to write from the sketch. You are summing at the base station the signals from all the users, and each signal is a MIMO. So you are summing MIMO signals. This is a vector in R by 1 at the base station. Okay, just like Y. You are receiving a vector. And this is sum of vectors. Because this is NR by NTK for each user. NTK. This one is NT by 1. NTK by 1. So we have outer dimension NR by 1. It has to be. Because this is NR by 1. We are at the base station. This is NR by 1. This has to be NR by 1 also. NR by 1. NR by 1. So please, you have no excuse to miss or to confuse the matrices, this notation. If we are concerned about the C sum, remember from scalar BC and MAC, we don't consider much the capacity region. We did the capacity region only for one case. MAC non-fading, only. That's it. All other MAC and BC, we did the sum capacity. Because it's what we care about as communication engineers. We are not interested in the capacity region. So we said it's involved now because you have to design the queues, the transmission matrix, you know, covariance matrix for each user. So it's not easy. If you have single user, it's trivial, probably. A single antenna per user, sorry. It's pretty trivial. خلاص, Q is scalar. And every user will transmit at his power. The multi-antenna case is more interesting. Now, Q is not B only scalar. Q is a matrix, you know. As I described before, go back to the recording, containing the diagonal elements, the powers of the NT streams, and then the correlation among these streams. So the optimization, this is an optimization problem. You have to solve it for all the Qs. As we have seen in the reading paper, the solution has to be iterative. Sequential, I mean, iterative. You do it for one user, and then you do it for the others. How? It's called iterative water filling. You do water filling, eigenbeamforming, and the SVD, sorry, and these things. But now it's not for noise only. It's for noise plus the other users seen as interference. Because remember, in water filling, you divide by sigma n square, isn't it? In is multiplied by sigma n square. We are normalizing here. You are dividing sigma n square by h square. Now, in here, no, you include the interference also, the other users. And the details are in the reading paper. What if that's the non-fading? What if you have fading with CSIT? Similar to single user MIMO, you do water filling in the eigen domain and in the time domain. Each time instant, know it this way, please, again. Each channel state, you do water filling, you know, for the users. Okay. And then another time state, you do water filling for the users. And you do water filling across time also. So we end up with joint space and time water filling. Space SVD plus water filling. Iterative water filling. Oh, this is what you need to know, please. If you want to read the reading paper more, something to explain it, please send me during the office, the office hours now, anytime. I'll explain it to you. Now, how about BC? BC is even more involved than MAC. In MAC, we know the capacity achieving scheme, which is iterative water filling. In BC, which has this model, it's from the base station to the users. And now we have multiple antennas at the base station. And at the users, we may have single antenna or multiple antenna. Please remember, whenever you have vector, think about the base station. Vector means the base station has multiple antennas. The users may have single antenna or multiple antenna. If the users have single antenna, we do zero forcing at the transmitter. So what does it mean? The base station has the burden of decolorating the streams. If you are not convinced about this, do the math. If you multiply by H inverse at the transmitter, and then you multiply H, the channel will multiply, you know, X by H or S, whatever you call it, you know, the transmitted, whether you call it X or S, then it will, the H inverse will lead to the identity matrix along with H. So it will decorrelate the streams. Again, it will have the same problem with So there is similarity. Zero forcing for, you remember, single user MIME or multiple streams? You have multiple streams in either case. But the multiple streams here belong to different users. There they belong to the same user, single user MIME. But they are independent. So it has a correlation issue if correlations are there. But you need power control here more than the case in the receiver. Okay, please. And I explained why. Go back to the recording. That's it. The cooperative communications is for reading, not, I wrote it reading clearly, not for the exam. It's interesting, by the way. So what's cooperative communications? You want to improve coverage, mainly. At least started this way. Release 8, 9, 10. One of the releases, I think. So we want to improve the coverage. It was adopted in 4G, if I'm not mistaken. So we have the backhaul link and we have the access link. So without, cooperative communications, we don't have this, which we call it relay, or distributed antenna. Can be relay, distributed ports in general. We want to reduce the access distance. Why? Now tell me, why we are interested in reducing the access distance? Wireless one.
For the attenuation, doctor, the path loss.
Yeah, the path loss is proportional to what mainly? Which
Distance.
parameter? Distance. And in 5G, we are 6G, we are going to beyond 5G. We are going to higher frequencies. So the path loss will be even more. We cannot change the frequency. We cannot reduce it. Unless we are in millimeter wave, for example, for high data rate communication. And I assume you explored this or you explore it in your project when you write introduction about 5G. Whenever you read about 5G, you will find millimeter wave. No doubt. It doesn't mean that 5G has to operate in millimeter wave, please, bands. But for broadband communication, usually in millimeter wave. For some other applications, it can be sub gigahertz, sub 6 or sub 1 gigahertz even. Some use cases for 5G. But assume we are at high frequency, so we have to reduce the access distance. And this is the key concept with cooperative communication, especially the distributed antenna. Why? Because the distributed antenna are connected through optical fiber, usually, to the base station. And they are used, I remember STC Mobile, they had projects where they implemented distributed antennas, some places, like stadiums, large malls, maybe airports, maybe some factories, Yeah. Now, they can be wired, they can be wireless. It depends. If it's difficult to do wired, it's not always easy to do wired, We know this, so we resort to wireless. If it's wired, we call it distributed antenna. If it's wireless, we call it relay, okay? This is the main concept, of the cooperative communications. So we are reducing the path loss through reducing the access link. They call it the access distance or the access link. Now, how do we design the relays? There are different classifications of relays, in band and distributed ports in general. In band, out of band, full duplex, half duplex, different types, fixed relays, moving relays, portable relays, and so on. We care about signal processing. There are two main types, amplifying forward. So the relay will act like a repeater, analog repeater, similar. We are in the digital domain, but it's a repeater. You receive the signal, you amplify it, and similar to analog. And you send it, whether it's uplink or downlink. What's the issue with this? It's simple to implement, but it will enhance the noise because you amplify both the signal and the noise. So it's good at high SNR. If you have high SNR, you can use amplifying forward relaying. A more effective one is decode and forward. So decode and forward, what do we do? Whether it's uplink or downlink, the relay will decode the signal. A clean version, maybe. It means you have, this is the benefit of digital, you have a clean version of the signal. And then it sends it back to the base station, or the other way, from the base station to the user. So, of course, decode and forward will be more reliable, but it will require, more processing. It will introduce some delay. Okay? So the relay decodes and re-encodes the received signal and then forwards it to the destination. User equipment or the BS. This type of relays is useful at low SNR. It's clear. Why? Always please think about the noise in communication. In communication, we think about the noise and the fading. They are the main impairments. We have. So we have to, design taking into account these effects. So when we care about the noise at low SNR, so it's better to use decode and forward for low SNR. More delay it introduces than amplifying forward, which would be an issue for delay sensitive surfaces like such as voice over IP. Also, the radio, this is the comparison, huh? The radio resources can be reused on the access link in case of two or more spatially spaced RNs please means relays, huh? Relay nodes per BS. Now, they have done with multiple antennas, a lot of work has been done about relays. Large amount of research. In general, the incoming and outgoing signals at the relay need to be sufficiently isolated using, this is a design issue. If you want to implement, full duplex, frequency multiplexing, out of band relaying, how you keep them out of band? If you want to operate at the same frequency, then the design is not easy. Yeah. I think you are following. Full duplex means receive and send at the same time. But usually in implementation, they split. They use FDD or TDD, huh? Half duplex in time or in out of band relaying in frequency to avoid interference, huh? Or you spatially separate the relay, transmit and receive antennas, but this is not always feasible. In signal processing, they have techniques to allow, and this is one of the schemes, by the way, one of the targets in beyond 5G is to implement full, they are interested at full duplex communication. You know the reason why they are so interested in full duplex communication as compared to half duplex? The reason is clear. Higher what?
Right, data rate.
Higher rate, yeah, clearly. It's double the rate. Because you are utilizing the same frequency at the same time. You are not dividing frequency or time. Remember, whenever you do orthogonalize time or frequency, you are reducing the spectral efficiency and the channel efficiency. Take it as a rule. If you do it simultaneously, it will be more effective. So they are strongly interested in full duplex communications nowadays. I'll not go into the capacity. Now comes information theory. No. Yeah, I'll not go into that. So I just wanted to introduce for you. And we are done. Okay. I received about quiz 1 a question. You know, what are the common notions of capacity are used for CISO fading channels, ergodic and, outage? Explain each of them. Are explained, as in the slides. Ergodic is average, and outage capacity is the maximum rate for a given outage probability. Specified outage probability. There are other notions, but we are not interested in them. Explain the transmission strategies for AWG channels for both CSIT and CSIR. What is it? What's the transmission strategy?
MRT? MRC?
No, we're talking about CISO.
Okay,
Which
okay.
one? What is it, Ahmed? Ahmed, what is it?
Again, doctor, what's this question?
We have CISO with CSIT and CSIR. What's the optimal transmission scheme? What did we call it? What power allocation scheme we use?
Water filling.
Yes, that's it. Simple. Water filling. With CSIR only, what do we do?
Equal power allocation.
Equal power allocation.
Equal power allocation. It's a piece of cake. Compare their capacities with the non-fading, At low SNR, CSIT is the best. At high SNR, CSIR and CSIR only are the same, and both of them are less than non-fading. Because at high SNR, fading is not affecting. Okay? Yeah. So it makes sense that CSIT will not be that helpful. So it will be like CSIR, and we know CSIR is always less than non-fading. So CSIT will be less than non-fading. And we have physical explanation. Again, at high SNR, fading is not that, important, and hence water filling will not be helpful. Channel states are similar. Yeah, it will not help much. Okay, this is quiz 1, quiz 2. The expression for, this is easy. Most of you, they did it. You substitute 0.15 here, and you solve for R. You move 1 to the other side, and then you take ln of both sides, isn't it? Please. It's very easy. I think almost everyone did it, as far as I remember. This is why the high average. Explain the differences between the capacity of CMO and MISO. I did it already. For fading channels with both CSIT and CSIR. Here, the answer is very simple. You can apply, it's very easy. If I were, student at, this is the editable version, of the quiz. I can do it in a minute. خلاص. MRC is equivalent to MRT. Done. خلاص. Simply. Yeah, we can do MRT. CSIT. So the capacity will be the same. And hence, capacities will be the same. That's it. As simple as that, CSIR only? No. So what's the answer?
CMO is better.
CMO will be larger. will be larger than C meso. As what? What's the explanation?
MRC all the time it can be performed, while
MRT is
isn't
not doable
feasible.
or feasible. Yeah, feasible is good. That's it. Almost done. To perform. Yeah. Done. That's it. Clear, guys? Yeah. I told you, if you know things, you understand things, it's not difficult to answer, you know. Clear now, ya Ahmed?
Clear.
Yeah. To be specific, both MRC and MRT are you know, implementable or doable or performed. Or doable. Or can be performed. That's it. Now, some of you they wrote it will be divided by L or by NT, the number of antennas at the base station, or you know, isotropic, and which is true also. It's another explanation. But this one is more clear, the isotropic transmission. This is what I mean by adding more details. I don't mind. We like details as engineers. But you have to tell me the main, you know, argument, the main statement of the answer. It has to be there. That's it. It's used for NISO. I would answer it this way if I were a student. Alas, you write this, you get a full mark. That's it. Clear? Please. The other quizzes, I think I sent to you already. We discussed them in the classes 3 and 4. Remember, we'll have a quiz with the final, isn't it?
Yes.
Did we agree on a quiz?
Yes.
Did we decide about this? We agreed, isn't it?
We agreed, yes, Doctor.
Yeah, and
Yes,
it will be
Doctor.
about the material, you know, of the single multi-user communication, you know, scalar or vector. Please. I'll complement the questions in the final. So, you know, it will be as if it were one of the questions in the final. So I'll move it to the quiz, additional question of the. That's it.
So
you know, the
material for the quiz will be Mac and the base station, right? Our broadcast.
multi-user,
Okay.
multi-user communication. Uh, the scalar Mac, scalar BC, you know, these two. The material after the midterm, you know. Yeah, these topics. The material after the midterm, simply. Yeah. Quiz material. So now I'll listen to your questions. I think I did what I have from my side. I wanted to tell, and I listen to your questions now. Please.
For the
Yeah.
handwritten slides, are they important?
Yeah. They are, of course, Victor, Mac, and BC. They are kept them handwritten because it's difficult to, integrate all the details in LaTeX. So I kept it, but they are clear. They are readable, is that? Yeah. Of course, they are important. The notes of Victor Mac and Victor BC are written.
Because I'm suffered with some letter, so take me a while
Why?
to understand it.
You mean the writing or the content?
And the handwritten.
Really? It's not readable?
For me, I'm just saying for me.
Let me know which parts, I'll try. So in the future offering, I'll base I can do it to LaTeX, the diagrams, and I'll write it as a LaTeX, but I can read it as a LaTeX, text. Is it readable, Abdurrahman, Mustafa, or everyone is struggling with it?
It's readable, but I need to spend sometimes, and
Oh, Abdurrahman.
because actually even the content
This is why
it's
avoid
new for
handwritten.
us, so I have to spend some time in order to understand actually the content.
No. I mean the readability. Content, of course, is in you.
Yes. Sometimes from the content, if I understand, I can read it.
Abdurrahman, it's readable, clear to you?
He stepped out for a while. He wrote it in the chat. He will.
Oh, I see. I didn't notice. Anyhow,
Sorry, sir.
please, Ahmed and Mustafa, if any part is unclear to you, I can read it to you, explain it.
For me, I'm able to
You
read it
managed,
now.
yeah,
Yeah.
Mustafa. Huh?
Yes.
Okay, Ahmed, please let me know if there's something to clarify. I can clarify it to you. Although I tried to make it readable as much as I can, but it's okay.
Most one from the equation, not of uh, the comment
Not the
or
text, you mean?
the description.
What's the issue with the equations? Please, yeah, take a snapshot, post it to me on Teams. I can explain to you which
Okay,
equation.
okay. Well,
Let
for the
me stop.
opportunistic, I'm fine with that. But for the
No, Victor
Mac,
Mac and Victor BC, please. They are important also. So I'll stop recording here and continue with you, huh? Please.
okay.
Yes, yeah,